we need to look into other protocol to do comparison. Here, we are going to use RIP as an example for our comparison. RIP is a routing protocol based on distant vector algorithm. Disadvantage of RIP emerge when it's deployed in large network, including slow conversion and poor scalability. I'll go through the limitation on RIP as well as the benefit of OSPF. But the main focus for today's discussion will be on OSPF, or Open Shortest Path, first. An SPF algorithm-based link state routing protocol was developed by IETF. OSPF can be deployed in large network to overcome RIP disadvantage. So how does OSPF meet the network expansion requirement? So let's have our discussion and start to explore OSPF. The main objective for this topic include understand RIP problems in large network. But more important is what is the solution. Here we have our solution by introducing OSPF. Now OSPF is quite a complex protocol, so we need to familiar the theory on OSPF characteristic, master the network type supported by OSPF. So we need to understand OSPF do have different network type, and we need to understand each network type on their characteristic and their behavior. Then by the end of this topic, you should able to know the process of how OSPF establish their neighbor relationship and their agency, and finally understand the concept of OSPF designated router and backup designated router. So let's look into the topic here. Challenges that RIP is confronted with a large network, and then we look into the basic principles of OSPF. Now first we look into the challenges in a large network. In this diagram we have three sites. This is our headquarters, branch A and branch B. Our network is keep expanding due to the service demand on the network. So when we have a huge network and expanding network, RIP may not able to cater for this expanding network. Second, we also have a challenge of higher network requirement. When there is a network fault, the network must be able to recover fast. So this is another challenge on using RIP. Third, we have a trend toward heterogeneity of network go up significantly. It means that we have to work with different vendor and different protocol. When this happens, we will have a complexity to integrate different vendor together. So we have all these changes in a large network, and we need a robust network routing protocol. We now look into existing RIP problem in a large network. The first weakness on RIP is hop-by-hop convergence. Let's look into N1. N1 has introduced to router A. Now router A will take some time to propagate this information to router B, and router B then will send to router D and router E. So it will take the time of T4 before router E receive this information. Hence, RIP is very slow in convergence and long failure recovery time, which means that if N1 fail, it also will take some time for router E to take note about the failure of the network. A second problem related to RIP is routing by rumors mechanism. In this case, router A need to update router B. Router B, after updates information, then will update router D. Router A will not send to router D directly. So in another word, router A doesn't update router D directly, but in return, it will first update router B, then B update router D. So here we have the rumors. So with this start of update, router will have lack of understanding of the global network view. So router only will have their neighbor information, but not their neighbors. And the third weakness of RIP is using hop count to measure the distance of the destination. If you look into this diagram, router A will send to router B, so it is one hop away. Router B send to router D, so again is one hop. So we have one hop here, one hop here. But router B also will send to router C and to router D. Now here we have our serial link and we have our gigabit link. So in theory, gigabit is so much faster than the serial link. Now, because it's using a hop count, router E will send to router D, and router D will decide router B is the best path instead of a router C due to the hop count. So the measurement based on hop count is not so sophisticated as in this example above. So we have a risk of selecting a suboptimum route. So here we have the three major problems related to RIP. But then again, RIP is a very simple protocol meant for a small network. So RIP is still surviving and is very good in a simple network if it is a home network or small network. So it's not entirely RIP is not used, but RIP is still being used in a smaller network. Let's look into solving RIP problem. The first problem in RIP is a slow convergence and long failure recovery time. RIP send the update every 30 seconds. So here it will reduce the failure recovery time as well as the update time. The solution for this is to use a trigger update, which means that once there is an update, this information will be updated immediately to the next router. So it will speed up the convergence time. This is where the OSPF trigger update come in. The second problem that we have is a lack of understanding of the global network topology. Now, as I mentioned on the earlier slide, router A sent to router B and router B sent to router C. So this is an update by rumors. It would be good if router A send it directly to router C, and router C is going to have their own algorithm to decide what will be the best way for me to reach router A. So the solution is a router independently calculate route on the basics of topology information. This is where we have the OSPF LSDB to calculate the best path, whereas in RIP we just based on the hop count on the rumors. And the third problem on RIP is the risk of selecting suboptimum route because it's based on hop count. Whereas we can have a solution, we do not use an hop count. Instead, we look into a total bandwidth as a criteria for us to do a route selection. Hence, we will have a solution for a topology like this. So if this is a slow link and we have a fast link over here and over here, so instead of using a hop count where I have to send to B, I can just send to the top router and send back because both of these are the fast link. So these are the solution, and the solution for this is using the OSPF. Let's look into the differences between RIP advertisement as well as OSPF advertisement. Now RIP is using distance vector, whereas for the OSPF we use the shortest path first. So first difference is OSPF separate the routing information propagation from the route calculation. What it means over here is, if let's say we look into the OSPF, they will send what we call the link state advertisement, and once they have all these LSA, you can see that they are in pieces, then they'll combine into one single pieces and they will be processed into the LSDB or link state database. Then we will use the shortest path first algorithm to determine what is the best path. Now, different compared to RIP, RIP is using the entire routing table from router A to the router B. So they also use a hop count. This is where the difference ends. So if you look into the router A send to router B, this is based on the periodic update, OSPF based on trigger update as I mentioned earlier on. Whereas on the OSPF, they don't send a routing table. They send what we call the link state update. And router B doesn't depend on router A to make the calculation. Router B use their own calculation going through the shortest path first algorithm to determine what is the best path. And the third difference is OSPF uses the accumulate link cost as the criterion for the route selection. Now this is important because if I'm using RIP, it's purely using a hop count. Whereas if I'm using OSPF, if I have two links, the first link is a gigabit and the second link is a serial. So each of the bandwidth have a cost. So for example, if it's a gigabit, the cost will be low. In this case, is a cost of 1, whereas for the serial, the cost is high. So maybe a cost of a 64, for example, or maybe even more. So when we look into OSPF, we look into the link cost. So once we accumulate all the link costs, that will become the best path in the routing table. So generally, we have 3 steps in our OSPF working process. The first step is to establish a neighbor relationship. This is very important. When two routers meet each other, OSPF have to be enabled. So router A will going to send to router B the hello packet, and router B will send to router A hello packet. Hence, they will form a neighbor relationship. I'm going to go into detail on how the relationship form, but this is the first step in the working process. Next, once the neighbor relationship established, both router is going to do a synchronization of the LSDB as I mentioned earlier on. Router A is going to send the link state advertisement to B, and router B will send a link state advertisements to A. Once the LSDB pieces are being sent, they're going to form what we call the database, or what we call the link state database. Alright, this is very important because once we have the database formed, we are going to run the shortest path first to determine what will be the optimum route. So this is where the step number 3, optimum route, are being calculated. As I mentioned earlier on, the OSPF are break down into 2 processes. One is the LSA, this is the first process, and second one is our control. This is where the shortest path first determine the best route. So remember, we have these 3 processes. And since we are on this slide, I also want to emphasize another things here is we cannot go to the second or third step if the first step is not formed. So typically, I will just do a display OSPF peer to determine that my peering is up. Then I'm going to do a display OSPF LSDB for me to check my LSDB, and display IP routing table to determine that my routing table is formed. So these are the basic command. Even though later I'm going to go into the detail, but for now, these are the 3 commands normally I will use in my mind to determine the OSPF working process. Note number 2, basic principle of OSPF. Here we will look into the neighbor relationship establishment. On this slide, we look into the concept of router ID. Each OSPF router owns a unique router ID which uniquely identify a router within an autonomous system. For example, in this diagram, I have 4 routers, and each of the router need to be identified. For example, here, who am I and who are others? I need to have a router ID, and the other neighbor also have his own router ID. So when we do a link state database synchronization, we know where this LSA came from. The format of router ID is a 32-bit IP address. Now, the preferred way for us to configure the router ID is to use a command called router ID. Now, this is a preferred way because we determine what is the ID of each router. For example, I can configure the router ID for this guy as 1.1.1.1. Here we have 2.2.2.2. So assuming that I do not have the router ID, okay, so under such a circumstances where we do not have a router ID, we can determine by the loopback IP address of each router. So assuming that this is my router A loopback has 1.1.1.1, so automatically this will become my router ID. So that will be a second choice. Now, if you do not have a router ID that is configured, you do not have a loopback, then lastly, we will depend on the interface. Assuming that now I have an IP address of 10.0.0.1 here, and I have a gig 000 10.0.0.2. So on the router A will determine what are all these IP address. So assuming that for simplicity, let's call this as 11.0.0.1 and 12.0.0.1. Now router A is going to determine which interface is going to start OSPF first. So assuming if let's say we are going to start the gigabit 000, this will become the router ID. But assuming that all of these interfaces are start at the same time, the interface which have the highest IP address will become the router ID. Now due to this reason, highest IP on physical will become the router ID. Now due to the IP address on the interface can change, so sometimes the router ID will run, and if you want to change the router ID, remember to reset to apply a new router ID. So sequence on choosing the router ID will be first based on the configuration of router ID. Second will be based on the loopback. If you have multiple loopback, the highest loopback will become the router ID. And third, it will choose the highest IP on the physical interface. Definitely the first one will be preferred because this is more deterministic. So this is the first thing that we do when we configure the OSPF. We now look into neighbor discovery and neighbor relationship establishment using Hello Packet. Now first, a Hello Packet performs the following function. The first function on the OSPF Hello Packet include discover a neighbor. An OSPF router can send a Hello Packet to discover neighbor on the link. Generally, OSPF uses two ways to communicate with the OSPF neighbor. The first way is using a multicast, which is the normal way of sending the Hello Packet, and the second way is using a unicast. Typically, we will use a multicast, such as in a broadcast network in the Ethernet, but if you are using a frame relay or using ATM, then most likely we have to use a unicast. I will go through this a frame relay OSPF in more detail on the next chapter. Now, second function of the OSPF Hello Packet is to establish neighbor relationship. Two OSPF router negotiate parameters in the Hello Packet to establish a neighbor relationship. Now the parameters is very important because between two routers, when they send the hello, inside the hello they have some parameters. Now a few of the parameters are very important. If router A and router B want to form adjacency, then their area need to be matched, which is the area ID. Then we have to make sure that the subnet need to be matched, and very important, the timer of the hello and the dead interval need to be matched. And finally, we also have a special area such as the sub area also need to be matched. Now these are the few information on the hello parameters that need to be matched to form a good adjacency. And third, hello packet need to use to maintain neighbor relationship. OSPF router use keep alive mechanism to continually detect the neighbor reachability. Now this is important because we have a dead interval, and that interval depend on how many hello packet that the neighbor miss. Once the neighbor miss certain number of hello, then is considered is not reachable. So the OSPF need to run the SPF to check what will be the next best path. We now look into OSPF neighbor relationship establishment process. In this topology, I have two routers, router A and router B. Now router A state will be in down state. Now this is a state where the OSPF have not received any hello packet yet. So once we enable OSPF on router A will send an hello packet with its own router ID 1.1.1 with a neighbor list of now, because there is no neighbor in my configuration. Now once router B receive it, router B would turn itself from down state to the init state. Router B about the same time send this hello packet to the router A. Once router A receive a hello packet from router B, it will also go into the init state. Now about the same time, router B who receive a neighbor of 1.1, remember that on the first step, router A send the hello, and router B upon receive this hello will put 1.1.1 in the neighbor list and send to router A. So router A upon receive this hello packet will change from the init state to a two-way state. Same thing go for the router A. Router A is going to reply with the hello packet with a neighbor list saying that, hey, router B, I just see 2.2.2 and this is my hello, and router B will change from the init state to a two-way state. Now the entire process of this hello are using a multicast. The reason is because this is a broadcast network running on Ethernet, and the multicast address typically will be 224.0.0.5. Still on the neighbor discovery and the relationship, now we examine a manual configuration rather than the self-discovery. OSPF allow routers to establish neighbor relationship using unicast hello packet. As mentioned on my earlier slide, OSPF when run on Ethernet typically use a multicast, which is 224.0.0.5. But when OSPF is running over frame relay or using ATM, we do not have any broadcast capability. This is where we have a MBMA, which is a non-broadcast multi-access. For this type of network, we need to configure the peer manually. So for example, router A need to determine that peer 2.2.2, which is a router B, is my peer, and same thing go for the router B as well. So if the network does not have the multicast capability, neighbor relationship must be manually established. This is always true in a frame relay network. Now after the hello packet, now we look into the link state information in detail. Here we look into the link state information. Unlike the route exchange process between RIP router, OSPF router exchange link state information. This link state information is to synchronize their links state database, and then they just forward this information to the next router. So A send a link state information to B, and if let's say B have a connection to router C, router B will also send the same link state information from A to B and from B to the C without changing any of this content. Eventually, all OSPF router will possess the same set of link state information. Now, link state information include link type. We have the interface IP as well as the subnet mask, who is the neighbor that's sharing the same link, as well as the cost. I will go into more detail on how to calculate the link cost in OSPF, but these are the information in our link state advertisement. Let's examine extensive data link layer support. Data link refer to a layer 2 supporting OSPF. A variety of data link protocol exist and their working mechanism differ. If we refer into this diagram, we have a serial interface. In this diagram here, we have our Ethernet in this diagram, and as well as we have a frame relay. Now each of these have a different network type. Typically on a serial, we will use a point-to-point, whereas for the Ethernet using a hub or using a switches, we are going to use a broadcast type of the OSPF, and if we are using a frame relay, we will be using MBMA. We also can use a point-to-point if we choose to, or point-to-multipoint. So we do have a different type of a OSPF. So this is the point-to-point, broadcast, MBMA, as well as point-to-multipoint. On this series of PowerPoint, I'm going to explain each of the type in detail. Here we have the first type, which is point-to-point. In this diagram, we have router A and router B connect over the serial link. So we can use a point-to-point network type. So using a serial interface, they do support broadcast and multicast. So we have no issue on using a multicast to do a OSPF discovery. Next, this is a broadcast network. This is the most common network you will see in the enterprise network. All these routers are connected through the Ethernet, so they may have to connect through a switch. So this is how logical it look like, but physically those routers are connected to a switch. Alright, so this is how physically they are connected to. So this is a logical diagram, and here we have a physical diagram. Now on the network using a broadcast, we do have a broadcast capability. So which means that we also can use a 224.0.0.5 to advertise our hello packet. Broadcast network is the most common that you will see in the enterprise. Now later I also will explain to you, due to the broadcast we also have certain complexity, such as selecting a designated router and the backup designated router. I will save that for the next slides. Now the third type is NBMA, or non-broadcast multi-access, typically used in an FR environment. Here we have our virtual circuit. So our virtual circuit have a DLCN number. So 103 from router A to router C, and 301 from router C to router A. We call it as a virtual circuit, and each of these have the virtual circuit. So which means that both A and B, A and C, and B and C have a full mesh. So it's a triangle relationship. Now since they have all these relationship, we can have a multi-access capability, but they are non-broadcast. This is where we need to configure the peer command that I mentioned a few slides earlier on. But as you can see that the frame relay is less popular nowadays. So the more popular one is still the Ethernet network, like this type of diagram, or the point-to-point network. So frame relay network is not really popular nowadays. And the final one on the OSPF network type is point-to-multipoint. So we can call it as point-to-multipoint. So a point-to-multipoint network is a set of multiple point-to-point network. As you can see from here, we have A connect to B through this particular VC, and A to C through this particular VC, 103, 301. You notice that between A and C, we do not have any virtual circuit. So here we have a point to a multipoint. Again, broadcast and multicast are supported. As you can see that this is really a point-to-point. As you can see that router A connect to router B as in one virtual circuit, and router A to router C as in another virtual circuit. So if we configure this as a default, the default setting will be in NBMA. For you to configure as a point-to-multipoint, we need to do it manually. We have to change this manually and not using a default setting. Once you change to point-to-multipoint, effectively it becomes 2 of point-to-point. Now because that the IP address are all in the same network, that make a point-to-point become a point-to-multipoint. Hence we have the broadcast and multicast are supported. Now anyway, the frame relay is not a really prime technology nowadays. We only include this as a completeness in your study of OSPF, so you won't caught yourself in surprise if you look into the OSPF running frame relay or ATM network. So let's look into the OSPF cost. OSPF cost calculation is based on this formula. The reference bandwidth is based on 100 megabit per second divided by the interface bandwidth. So assume that we are using 100 megabit as well for our router, then our cost is 1. Now integer number 1 is the lowest that we can get. So assume that we have a 100 megabit per second as a reference bandwidth, and my actual interface is 1 gigabit, which is 1000 megabit. That will become 0.1, right? So the cost of OSPF cannot have 0.1. The minimum that we have is 1 only. So in this case, regardless of 1 gigabit per second or 100 megabit per second, the cost, both of them are equal to 1. All right, so in this topic, we look into how to calculate the cost. So the cost can be changed in two ways. The first one is to configure the cost directly under the interface. So we have to go to the interface and we have to change the cost directly, regardless on the interface bandwidth. Now, second way for us to change the cost is to change the reference bandwidth. Just now I did mention to you saying that the reference bandwidth by default is always 100 megabit per second. So by changing the reference bandwidth from 100 megabit to, let's say, 1000 megabit per second, so now if I'm using an interface, let's say now I'm going to use a 100 megabit per second, so I will have 1000 as a reference divided by 100, which give me a cost of 10. And if I'm going to use a gigabit divided by gigabit, then the cost is 1. So now I have a 100 megabit and I have a difference on the 1000 megabit. So there is a difference between a gigabit as well as 100 megabit. So this is the second way for us to change based on the reference bandwidth. In this diagram, we have three routers. We have the router A, where we have the G1 here, where is the cost of 1, and we have the G3 here, which is a cost of 1 as well. Now we have a loopback. Since the loopback is connected to router C and is internally, so the cost is equal 0. Now if you look into this statement, accumulated cost from router A to subnet 192.168.3.0/24, which in this case this network, is equal to G1 cost plus a G3 cost. So we have a G1 cost here plus a G3 cost. So if we never change anything, we leave as the default formula, which is the reference bandwidth as 100 megabit and the bandwidth is even gigabit. The cost is still 1. 1 plus 1 equal to 2. So this is how we calculate the cost. Now, as I also mentioned that we can change the cost. If I'm going to change the cost of G3 to 2, then I will have 1 plus 2. So in this case, it will become 3. So we can manipulate the cost as we wish. Need to look into the detail of OSPF packet header. On this packet header, we have the IP packet where we differentiate by using the protocol number 89. Then we have our OSPF packet header, and we also have OSPF packet data. So let's examine our packet header. The first in our packet header is the version. The version, if it's on OSPF IPv4, then the version is number 2. If it's an IPv6, then the version will be 3. Next, we look into the type. The type here is to indicate what is the OSPF packet. Now, packet length is indicated by byte. So here, this is the length of the entire OSPF packet length in byte. Next, we have the router ID. As I mentioned in the very beginning, router ID is very important for us to identify the OSPF. So we can use a router ID of the VRP command. We can use the loopback, or we can use the highest IP address of the interface. Then we have the area ID. So this is where we have the 32-bit of the area ID. Then we have the checksum. Now checksum is used to verify the data integrity of the OSPF packet. If the checksum fail, then the OSPF packet integrity is compromised and that will be discarded. Next, we have the authentication type. The authentication type here, we have a few value. So it can be a 0, means that this is a no authentication. All right. Then we also have a value of 1, where we are using a simple password. And we also have a value of 2, where we are using MD5. Okay, so that is the authentication type. And finally, we have the authentication. This is the authentication value. Here I have a OSPF MD5 packet catcher. So I'm going to look for the OSPF. All right, so I have an OSPF packet here. Now let's look into the IP protocol IPv4, first we need to look into the in this case the protocol number. So as you can see that this is a protocol OSPF IGP 89. So that is our indicator that this is a IP OSPF. So let's look into here the OSPF packet. Now this is our header that I mentioned earlier on. First is the version. This is a version 2. Then the message type here. This is a hello packet. So we have a database descriptor packet. That is a type. We have the link state update, link state request. I'm going to go through that later part. This is a packet length which is in byte. Then we have our router ID. So here we have the router ID of 10.0.0.1. This is a backbone area 0. As you can see that the checksum is none. Now this is the authentication type. Remember just now I mentioned that we have a 2 here. 2 means that this is a MD5. And over here we have the MD5 key 1. That's the authentication cryptographic data number 16. As you can see that this is a MD5. All this information is encrypted. So this is where the authentication field located. So instead of just opening the OSPF, so we are now dissecting the packet. So these are the packet, how it looks like. If I go further, rather than just the header, I can even look into the hello packet. As you can see that these are the information that's inside the OSPF hello packet. Now I'll go through this in more detail later on, but for now just remember this is all the information that's located on the header. Let's look into the detail of the packet type. As on the earlier demonstration, I mentioned the packet type. We have the hello. If you notice early on the video, the packet type you notice is a type number 1. So on the first column, we have 5 type 1 until 5. Hello packet is to discover and maintain OSPF neighbor relationship. Now this is very important because this is the first packet they used to negotiate the parameters, and as I mentioned on the earlier slide, there are certain parameters that need to be matched, else the neighbor relationship will not form. Now type 2, we call this as a database descriptor. This packet is used to describe the content of a local link state database to neighbor, so the neighbor can determine whether the LSDB are complete or not. So it's normally used during the exchange of the LSDB summary. Then we have a type number 3. We call this as a link state request packet. LSR is used by the router to determine whether its link state database is complete compared with the information in the database descriptor packet from its neighbor. So if the LSDB is incomplete, it will create a list of link state advertisements that need to be obtained from the sender of the DD packet and then sent as a link state request. Then we have a type 4, we call it as LSU or link state update. Now as its name suggests, when LSR is being sent from the neighbor router and the responder router have to send the LSU, in this case I have to answer, this is the update. So this LSU packet are sent to the neighbor and the LSDB synchronization among all router in the area. So this is where we have the LSU, which is the answer. And finally we have the type number 5, which is the LSACK or link state acknowledgement, which the router used to acknowledge the receipt of link state advertisement in order to ensure the link state synchronization is reliable. So after you understand about all the OSPF packet type, let's look into the functional requirement of OSPF packet. Now first function to be achieved using OSPF packet is to develop a neighbor relationship as well as for you to maintain the neighbor relationship. And for that, OSPF use the hello mechanism. So different compared to RIP. RIP use a periodic update and they do not have any hello mechanism. Now next, OSPF have this link state advertisement synchronization. These two enable two routers to send the link state advertisements to each other for LSA synchronization. If you still remember earlier on, I did mention the packet type as in first is a database description, then we have a link state request as well as the link state update. So the link state advertisement synchronization is fast and few resources are consumed as compared to RIP. We just simply give out the entire routing table every 30 seconds. And finally, the function of OSPF packet have to be reliable. And that is being ensured by using the link state ACK or advertisement. So we have a reliable link state advertisement synchronization. So all in all, you can see that OSPF protocol are more reliable as well as more robust and can scale better as compared to RIP. Now let's look into the LSDB synchronization. Here we have the second part of our process. We have a router A and router B. Router A have a router ID of quad 1 and router B have a router ID of quad 2. Now remember, on the first part, both the router will send an hello on both sides. So A will send to B and B will send to A. If you still remember, the process is from the down state into the init state. If let's say this is a frame relay, we also will have an attempt state. Alright, so for our case here, init state will go into the two-way. Once after the two-way, the state will become the X start state here. So let's follow back into our process. Right now, router A is going to send a database descriptor from the router A to router B. Now inside the database descriptor, we have the sequence. In this case, we have the X-axis sequence number. We have a bit which is I. I stand for init bit. Now this init bit will set as 1, and this is the first in the sequence of the database description packet. Then we have the M. M stand for a more bit. More in this case indicate that there are more database are follow, and MS stand for the master or slave bit. Now when router B also send the database descriptor at the same time, now please remember that these two DDR send about the same time. Now router B have a router ID of 222 will reach router A. Router A, router ID of 111 will also reach to router B. Now this is where we have the X start state. Now once the router A receive router B sequence number of Y as well as the router ID of 222, router A is going to compare 1.1.1 versus 2.2.2. When it look into 1.1, which is this router A router ID versus 2.2.2 router ID, 2.2.2.2 is larger compared to 1.1. So in another word, router B is a master and router A is a slave. With this decision, the X start that we have, which is go into the exchange, router A in exchange state is going to send a database description following router B sequence number. So instead of X earlier on, now router A is going to follow router B of a sequence Y as indicated over here. Now router B upon receive it is go to X start to exchange state. Now router B, which is still on the exchange state, acknowledge that by sending a sequence number of Y plus 1 to router A. So assuming that this Y, let's say, is 200, so stage number 3, 200 will send to B. B will send 201 because it's plus 1 back to A. That is step number 4, and now router A is in exchange state. Now in between, we also have the link state request, update and acknowledgement, and once that is being done, exchange state will go into the loading state, which is using 1 Y plus 1, and exchange will go into the full state of router B. Now let me illustrate the entire process over here by looking into my Wireshark. Over here, I have a Wireshark between two routers. So in this case, I have router A connect to router B. Router A IP here, we have 10.1.12.1, and here I have 10.1.12.2 as indicated over here. So we have number 1 sent to number 2. Now as you can see that this is an OSPF packet. So let me expand this OSPF packet. So we have the OSPF, that is our header, and here we have our OSPF database description. As you can see from here, the message type is a database description. Let me expand this and put this into alright, so here we have our message type. That is our database description. As you can see from here, number 1 sent to number 2. So the router number 1 router ID is 1111. And if you look into the database description, you can see that this is my bit. Here I have the init bit, which is the I is being set because this is the first in our database description. Then we have more that's coming, that is being set, and router 1 declare itself as a master. Now let's look into the second frame here on the database description. As you can see that this is a sequence number of 64. Router B also set I as 1, more as 1, and is also claimed that it's a master. So if I look back into the router 1, the sequence number is 401, whereas router 2 sent to router 1 sequence number is 54. 2.2 versus 1.1, 2.2.2 is larger than 1.1. So in return, router 2 are supposed to be a master. So if we look into the frame number 12, as you can see that here the master is no. And you also notice that the sequence number is 54. In here, router 1 follow router 2 sequence number. Let me go back to number 11 here. You can see that it's 54. Number 12 is also 54 because originally router A sequence number is 401. So here we have the sequence number of 54, and you also notice that router 1 master bit is set to no, and on the frame number 13 I am the master and I include one more sequence number, which is 55. Okay, and finally on the frame number 14 here related to the OSPF, here I have 55. So this is the entire trace on the database description. Let's continue and complete the LSDB synchronization. Now router A will send an LSR or link state request packet to router B to request more recent link state advertisement that has been discovered in the exchange state but have not yet been received. Router B then provide router A with the link state advertisement in the link state update. On receiving this link state update, router A transition the neighbor state from the loading to full. Then router A will return an link state LSK, which is the acknowledgement packet, to router B as an acknowledgement for the received LSU packet. When router B receives the acknowledgement packet, a full adjacency is established between the two routers. So these are the process on how the OSPF LSDB synchronization work. We now look into OSPF enable state machine. Generally, we have a 7 state, except if we are in the NBMA, we should have one more state we call attempt state. Let's look into the detail on each of the state now. So first we have the down state. This is the initial state of a enable conversation. It indicates that the router has not received any hello packet from its neighbor. If we are in the NBMA, a router can send hello packet at every pull interval to its manually configured neighbor, which is in down state. So if we are in the attempt state, it indicates that the router has not received any recent information from its configured neighbor, but that it has been sending hello packet to its neighbor every hello interval. If the router does not receive any hello packet from its neighbor within the router that interval, the enable state will go back into the down state. Next, we have the init state. This state occurs when the router receives a hello packet from its neighbor but does not see its own router ID in neighbor list of this hello packet, which means they have not established a two-way communication with each other. In this state, the router ID of all its known neighbor must be included in the neighbor list of the hello packet sent by the router. Next, we have the two-way state here. Now, in two-way state, we have an event where we have one-way receive and two-way receive. Let's look into the two-way receive here. This event occurs when the router sees its own router ID in neighbor list of the hello packet received from the neighbor or receive a database description packet from the neighbor. If the router needs to establish an adjacency with a neighbor, the neighbor state transition to Xstart. Now this is assumed that we have a two-way and the LSDB synchronization will begin. Otherwise, it will still go back into the two-way state. Where if we have a one-way receive, this event occurs when the router finds its router ID is not contained in the neighbor list of received hello packet. This is often due to restart of neighbor router. So assume we do receive a two-way hello, then we will transition from a two-way into the Xstart state. In this state, the router will start to send a database description packet to its neighbor. The master and slave relationship is established, as I explained earlier on, and the initial DD sequence number is determined. Remember that the init bit is set to 1. So if we are in the Xstart state, this is the first step toward forming an OSPF adjacency. Now next, assuming that the negotiation is done successfully, then we will go into the exchange state. This state occurs when the router exchange with its neighbor database description packet contain the link state advertisement summary information to describe its entire LSDB. So when two routers exchange DD successfully, we are in the exchange state. From the exchange state, we will go into the loading state. This state occurs when the router sends a link state request packet to its neighbor requesting the more recent link state advertisement that has been discovered in the database description packet during the exchange state. Subsequently, the router receives the responding link state update packet from the neighbor. And finally, we will have the full state. In this state, the link state request list is empty, which means that all the LSDB is synchronized with its neighbor and it indicates the full neighbor adjacency. So here we have all the state on the OSPF neighbor state machine. We look into the link state advertisement header now. In this diagram, we have the OSPF link state information. The top here, we have the bit. So we have a 0 bit all the way to 31. So here indicate 32 because we start from a 0. So 0 to 15, which is 16 bit. This is where the link state H reside. This H is the link state advertisement in second. Next, we have an option. This is a capability of the router. Then we also have the link state type. This indicates the LSA format and function. We have different types such as a type number 1, number 2, number 3, number 4, number 5, number 7. These are the common type that we will use. I'll go into the detail LSA type later on. Next, we have the link state ID, router ID. Then we have the advertising router. This indicates the router ID of the router that originate the LSA. And then we also have the sequence number. This is for the OSPF to detect old and duplicate link state advertisement. We have the link state checksum to check the integrity of the LSA. And finally, we have the length of the link state in byte. So let's look into the Wireshark that I prepared for you. Here, let's look into one of the update. Alright, so we have our link state advertisement over here. First is our age. So we have 1 here indicate that is 1 second receive. Then we have our option. So this is a capability of the router who advertise this LSA. Okay, so this router do support the external. So this is the option. Then we have the type. So this is a type 1. As you can see, it's a router LSA type 1. Then we have the link state ID, which is our router ID, the advertising router ID. Then we have the sequence number, checksum, and this is a blank, which is in this case 60 byte. So here we have our LSA header on the OSPF link state information. Lastly, on this topic, we look into the designated router and backup designated router election and role. Now first, let's look into the problem in multi-access network. Managing n times n minus 1 divided by 2 adjacency is complicated. What does it mean by this? If you look into this diagram, I have a router A connect to router B and router C and router D connected logically over the multi-access. They are running on a switch. Each of these router A, B, C, D are connected through a common subnet. Now because they are using a common subnet, let's say this is 10.0.0.1, this is 10.0.0.2.3 and .4. Now each of these router able to connect together. So when the OSPF hello packet is being sent to a multi-access network, they are going to form a adjacency. So as you can see from here, we have all these adjacency. If we count the number of adjacency, we have 1, 2, 3, 4, 5, and 6. So based on this formula, if we have 4 routers times by 4 minus 1 divided by 2, this is exactly we get number 6. Correct? So this is where the complication occur. So if we are going to have let's say 10 routers in our network, that will be 45 adjacency. That is massively complicated. Now due to this reason, the LSA is going to flood repeatedly to the same router again and again, and this will be waste of resources. We need to find a solution for this problem. Hence we have a concept where we call it as a DR and BDR. In this diagram, it's the same like the previous diagram. What we need to do is to elect what we call a designated router. All the router will going to form with the designated router. So in our case here, we have 4 OSPF router. One of these will become a designated router. All the router is going to send LSA to router A in this case. So assuming that router B is going to have a link state advertisement is sent to router A is going to send to router C and router D. So now router A become a designated router. We also call it as a pseudo node. So in a multi-access network, the DR is responsible for establish and maintain adjacency and flooding of a LSA. So with the concept of a DR, the number of LSA will greatly reduce. How do we avoid the DR as a single point of failure? Which is true, because if I have only one DR and everyone form with a DR, what will happen if the DR fail? So this is where we have a backup. So we are going to have a DR and BDR. In the event the DR fail, well, router C and router D we're going to send to the BDR. So in another word, if I'm going to redraw this diagram again, if I have a DR and a BDR here, DR and BDR will always form adjacency. Okay, so router C and router D will form to DR. Router C and router D will also form with the BDR as well. So we have a full adjacency. Now between router C and router D, this is considered what we call the DR others. Now DR others to the DR others, they do not form adjacency, they do not, alright? So they only form two-way relationship between them. So let's look into this in more detail on how to select a DR and BDR. Now let's look into the DR and BDR election. So the election rules will be follow these two rules. The first one here is an interface with the highest router priority will take precedence. In this diagram, we have the 4 routers as in earlier topology. This number indicate the priority. Now, priority of 100 is a default. Based on the first rules, the highest router priority take precedence. 200 priority should become a DR, but in reality, router D is a DR others. So how we can reconcile with the above statement? Well, remember, router D, even though have a highest priority, does not necessarily become a DR or BDR even it has the highest router priority. The reasons being, among all the 4 routers, router A start first. When router A start the OSPF faster than the rest of the router, router A now become DR because it doesn't see any one of its neighbors start. So you will become a DR. Then router C start second. So since you are the DR, then automatically router C become a backup designated router. Now router B and router D, it really doesn't matter who starts first because we already have a DR and a BDR. But I have to emphasize here, when we have a priority of 0, 0 priority is always ineligible to become either DR or BDR. So in other words, router B do not want to be part of a DR BDR election. Now rules number 2, if the interfaces have the same router priority, where if I have 100 and I have 100, assuming the interface with the larger router ID will take precedence. So this is a tiebreaker. Now with this concept, I want you to remember that it will always better to configure the priority to be higher on the router who have the highest capability to become a DR, and those lower capability router, maybe the RAM or the CPU is not as good, configure that as a 0. Now if you want back the router D to become a DR, what you need to do is just to reset the OSPF process. I'll show you in the lab later. In OSPF implemented by Huawei, we have 4 network types. The first one, we have the point-to-point. They will form adjacency. We do not have DR BDR because it's just a point-to-point. If we have a broadcast or non-broadcast multi-access, then we will have a DR established adjacency with the BDR and DRs others. The BDR establish adjacency with the DR and DR others as well, but the DR establish only neighbor relationship with each other. Now please remember here, even though it said that it's established neighbor relationship, this is not a full relationship. It is just a two-way relationship. Whereas for the DR to BDR, it will establish a full, and BDR to the DR others also will become a full relationship. And finally, on the point-to-multipoint network type, we do have a full adjacency. Once the adjacency is established, the LSDB synchronization is complete, then the router will start the shortest path first algorithm to calculate the shortest path to the known destination on the basis of the information in their LSDB. So this is very important. Here, before ending our topic, we have a quiz. Which of the following packet are OSPF packet? So the answer for this are A, hello, B, database description, C, link state request. There's no such thing called link state DD and link state advertisement. We only have 5 types. The other 2, which is link state update and link state acknowledgement. So these are the only 5. There's no such thing as link state DD or link state advertisement. It's only acknowledgement. Now second question, describe OSPF network type. We just have described early on. We have the point-to-point, broadcast, NBMA, and point-to-multipoint.